Right, this is a distinction question. Reason being a distinction question, there is a little bit of integrity to it. Basically what we've got to do here is really look at integration and compare it with the numerical method as well. So there's a bit of a justification comparison at the end. Let's take it from the beginning. We've got a rotating cylinder, so it could be a drum, it could be a washing machine, or it could be a wheel, in fact anything like that. But this is the angular velocity W, yeah? It really is a Greek letter actually called omega, just like a W, omega, but we'll just call it W. And this is the equation they give you for the angular velocity. What they want you to do is actually find the constant of integration and hence the equation for the displacement of this particular cylinder. They do give you the displacement. Remember, the displacement is not meters this time, it's actually radians because it's a rotational, or it's an angular distance. The angular distance can be measured in degrees. It could be measured in degrees, but we actually measure it in radians in sort of mechanical engineering. We're given a time of 5 seconds, and then we go through the whole process. So we've got the equation W, or omega 3t squared plus 4t plus 5. Now remember, this time we've got to integrate it to find the angular displacement. We've got to integrate this particular velocity, so we'll put the integration sign there, you know, put the integration sign with respect to t, which is the time factor, and add one on and shove it on the bottom. Remember, add one on and shove it on the bottom. So effectively what we've got is 3t3 over 3 plus 4t squared over squared plus 5t. Yeah, but don't forget the constant of integration is c. So that's well on the way now, but again we can sort of, you know, we can simplify it down. These will cancel out, so you've got t3 plus 2t squared plus 5t plus c. Okay. Now on this particular sample here, or this question, they do tell you this is 400 radians, you see. So what we can do is literally put 400 there. And they do tell you the time as well. They tell you the time was actually, let's have a look. Yeah, it was 5 seconds the time. So what we'll do is now is put 5 seconds there to the power of 3. That's a 3 there. 2 times bracket 5 squared plus 5 times the 3 seconds there. Oh, and we don't know him. I wonder why we don't know him. We know everything else but him. But if you remember the question, it says you want to find the constant of integration. So in fact, what we can do is transpose the equation at the very end to find the value of c. Okay, so if you work this out, 5 to the power of 3, 5 5s is 25, and 25 5s is 125. Don't do 2 times 5. No, it's 5 squared first. 5 squared is 25, times the 2 is 50, plus your 5 times 3 is 15. And then what we'll do is we'll go from there. So I'll just write that down for you. So we'll just write this down, keep it all consistent. So we've got 400 is equal to 125 plus the 50 plus the 25 plus the c. Lo and behold, if you add all that up, you get 200. Yeah. And what we'll do for transposition, this here is a plus, turns to a minus on the other side. So we end up with 400 minus the 200, which in fact is 200, which is part of the answer, or the first answer for part A, which is the constant of integration 200. Okay, that's basically the idea around that. Now, the next part, we've now got to plot a graph between 0 and 3, and use the trapezoidal rule to find out the area under the graph. So let's have a look at this one. Okay, so we'll clear that. We'll change the colour a little bit here. So basically, what the best thing to do really, I'll just do this rough, it doesn't really matter too much about the presentation. The time value, it only said between 0, 1, 2 and 3, so we'll just go for that, 0, 1, 2 and 3. It could tell you quite a lot. Yeah. And the other thing is, they want you to find this angular velocity omega. But if you remember, the equation for omega was 3t squared plus 4t plus 5. Okay, So for every single one of these, we put it in here, you see. So watch this. 0 there. 0 squared is 0. 3 times 0 is 0. 4 times 0 is 0. Plus 5. So in fact, there is a 5 there. I've seen students put 0 in there because they get carried away. That's 0, that's 0. Oh, put 0 down. Be careful. He stands alone. He stands alone. If you put the 1 here, 1 squared is 1. 1 times 3 is 3. Plus 4 times 1 is 4. So that's 7. So plus the 5, so that would be 12. 2 squared is 4. 4 threes is 12. Plus that 8 there, that's 20. So that would be 25. And finally, 3 squared is 9. 9 threes is 27. Plus the 12, 39. Plus the 5 is 44. So just by looking at that, we've now got a sort of table which we can plot a graph. Okay, so how do you plot this graph? Right, so very basically, very crudely at this point, what we will do is we'll put the t values on the bottom and the angular velocity w or omega on the vertical axis. Yeah. Now what you've got to do here is you've got to keep the strips equal width. So we've got 1, say that, 2 and 3. These must be equal here. Very important that. And what we'll do here, see the big value is 44. So if we stuck 45 here, possibly go up in 5s, you see. 5, 10, 15, 20, 25, 30, 35, 40, 45. Okay, you've got the idea. And what we do is plot the graph. So when it was 0, t, this was 5, so that's here. Hear that? And when it was 1, it was 12, so 12's about here. And when it was 2, it was 25, which is about here. And finally, when it was 3, it was 44, which is just up here. See that there? And then you go vroom like that, and you produce the curve. Now this is called the trapezoidal or trapezium rule for a very important reason. What you do is you drop a perpendicular down here, and here, and here. And what you would do at school to work the area of the graph, you count all the little squares up here and work the area under the graph. But the trapezium rule has actually got an equation. We can work the area under this graph by actually using this equation. So basically what it is, it's the strip width. This is the trapezoidal method or numerical method divided by 2 times the sum of the first and the second ordinates, yeah, the sum of the first and the second ordinates plus the remaining ordinates. I'll just put remaining ordinates times 2, yeah, times 2. Don't forget that 2 there. So, right, well, the strip width, if you remember rightly on that graph, it was 1, you know, 1, 2, 3. So the strip width is 1, so it's 1 divided by 2 times the sum of the first and the second ordinates. If you remember rightly, there were 5 and 44 on that graph, so on the table. So the 5 and the 44 goes there, so we've now got 49, yeah, plus the remaining ordinates were the 2 in the middle, the 12 and the 25, which is 37. 37 times the 2 there, so that's your 74, yeah. So we now got, what's that, 1, 2, 3 times your 0.5, that's your half, isn't it? So we end up with 61.5 as the answer. Alright, that's the numerical method of integration. We could have used the mid-ordinate rule or we could have used Simpson's rule, but we chose the trapezium rule simply because it was in the question. Right, we're 3/4 of the way through this distinction question. We've now got to do it in an accurate method. An accurate method of working out the area. My guess is that'll be close to what we want to do, but this is only approximate. Okay, so finally what we will do now is do the actual integration situation. So if you go back up to w is equal to the integral of 3t squared plus 4t, if you remember this, plus 5 dt, we integrate that, yeah, we integrate it. So we end up with t3, I'll do all the cancelling, we've done all the cancelling and everything, yeah, plus 5t. We don't need to put the constant of integration because we've now got, in fact, a definite integral. A definite integral between 0 and 3. Remember the 0 and the 3 there? Yeah, so we've got between 0 and 3. So what we'll do is we'll put the 3 there and the 0 there. Now if you remember earlier on, I says we can put these into two sums now with a big minus in the middle, that minus there. Okay. And what we do now is literally put this here and this one here, can you remember? And this one, the big one at the top, goes on this side and this one goes on this side, and then we get the answer, and then we'll finish. Well, we'll actually compare the two answers. So let's go for it. We've got 3 to the power of 3 plus 2 times 3 squared plus 5 times 3. All we've done is substituted the 3 into the t. On the other side we'll substitute the 0 into the t, so that's 0 to the power of 3 plus 2 times 0 squared plus 5 times 0. This one's going to be nice on the right hand side. Nothing cubed is nothing, nothing squared is nothing, nothing times 2 is nothing, 5 times nothing is nothing, so great, that's nothing. Right, but we still have to prove it, yeah? 3 3s is 9, 9 3s is 27, right, 27, yeah. 3 squared is 9, 9 2s are 18, plus your 15, yeah, and I make that out as 60, yeah, that will be 60. Compare that with the previous one, which was 61.5, I believe. Yeah, it was 61.5. This is the business. This is the business. This is the one where you get an accurate measurement of the actual answer itself. People say, why is that? Well, if you think about it, if you go back to that graph, we said the area of the trapeziums. Can you see the curvature there? The curvature there gives you a slight error. If you do a trapezium, remember a trapezium's got parallel side here, you know, two parallel sides there, you're going to have a little bit of sort of, you know, there's a bit of a curvature there. So this takes that curvature into account. This gives you the exact answer. I wish you very well in your studies. This is a typical distinction question for the Unit 28 Further Mathematics. Thank you.